Hello fellow problem solvers. So today we're going to be doing a problem from the Elmo 2020, problem number 1. I suggest you try this lovely function equation problem out. I really like this function. It's a medium difficulty, medium to easy difficulty function, I think, that I invite you to try out for a minimum of 20 minutes, ideally an hour, not more than 2.5 hours. If on the other hand you'd like to go along with us, give it a go for the next 10 to 15 minutes. I really invite you to give it a go. Because if you haven't really had a lot of experience with this iterated f that we have here as the definition of the function, then this is going to help build that up for you. So let's see what we have. We have for every x, y, and z that are in the positive integers or natural numbers, we have that x plus y plus z plus 1 is equal to f of z that's applied f of y that's applied f of x times, right? So there's a lot of stuff here. And the first sort of idea is to say, okay, let's see what is this? So we have, what happens when we have fk of something x is equal to fl of the same thing? Right, what does this mean? And the answer is, we don't know yet. But it seems like in this specific problem, the way it's set up, it would be pretty nice to look for some injections, right? Because I can just switch things around and I'll have an injection. And in fact, if f of a is equal to f of b, then f of a applied and then f applied any k times is going to be f of b, where f is applied k times. And now if we set k to be equal to f of x of y, then here we will have that y plus x plus a plus 1 is equal to y plus x plus b plus 1, i.e. a is equal to b. So now with that, if we have so now this means we have an injection. And now if we have f of x applied k times is equal to f of x applied l times, like an injection is really just getting rid of one of the f's. Like if we have f of x equal to f of y, an injection just says I can get rid of one of these f's and I'll get f of x is equal to y. That's what an injection is really doing. If like in a sort of rule of thumb way, right? That's what an injection is doing. So here we can decrease this by 1, right? And then we can keep on decreasing it until we get an f here and an f of, say, k minus l plus 1 here. Say k is greater than l. Like if they're equal, then it's not really much. But if they're different, it's interesting because we can get them to be different here. So now here I invite you to pause for another 10 minutes and try to push the problem further and see how far you take it. And now here's the next sort of idea for me. Okay, let's see what this is. So I can keep decreasing it. And when I get f of k minus l plus 1 is f of that of x. f of x applied k minus l plus 1 times is equal to f of x. I kill the f again. And that sounds a bit harsh, kill the f. But what I get is that this implies f of k minus l of x is equal to x. So this is what I can get if I ever have fk of x is fl of x. I don't know how to call this. So I have this absolute value thing. And it makes sense, like, because if k is equal to 12, then we have f0 of x. f0 of x is usually thought of as x, right? It's f applied 0 times. That's what this thing is telling you. So now, with the problem, this means here's the thing. We have symmetry here. We don't have symmetry here. We have symmetry with respect to x, y, and z here. Here we do not. So what do we do then? Well, we say, I like the fact that there is symmetry here, but not here. Let me take advantage of that. Let me switch x and y. And what happens then is that we get that f of z of what? We have fz of f of x, y minus f of y, x is going to equal z. Now, pause for another, 5-10 minutes, see if this tells you anything. And here's what it tells me. What is the solution here? It's not f of x is x. It's f of x is x plus 1, because I'll apply this. Then that I'll have f of y applied x times. I'll have a y applied x plus 1 times. And that will give me y plus x plus 1. And then I'll have this applied y plus x plus 1 times. And that will give me x plus y plus z plus 1. That's sort of the idea. That's how, for me, I was just like, what is a simple, let me try a linear thing. A constant does not work. So let me try a linear sort of combination. A linear combination that does work is that. Ergo, let's prove that it is that. But in that, there's no f of 1. And also, it's important to check different types of linear combinations in general. Ax plus b as a general solution for f of x. Even sometimes quadratic, if you have an idea, it could be a quadratic. Sometimes it's something completely different. You have to check it out. But this just gives you an idea, a hint, sort of what should I look for. Now here, this tells me nothing is going to be 1. There's no f of a which is equal to 1. The smallest f is 2. And here I have a z. So if I have z is equal to 1, I can force this to be 0. And now let's try to prove that there's nothing that can be 1. So if f of some a was equal to 1, then if I said x equals y equals a, what would I get? I would get 1. So it's f of a applied once, that's 1 again. And I could have set z to be equal to f. I'd have f of z is equal to 2a plus z plus 1 for every z. But also just setting z to be equal to a, I would have 3a is equal to, actually I'd have a 1 here. The 1 would cancel out. 3a would be equal to 0. A is 0. That's not in the natural numbers. And so what we have is there's no such a such that f of a is 1. So plugging here, z is equal to 1. That gives us this thing up here. It can't be greater than 1, right? This thing cannot be greater than or equal to 1, the absolute value. So we have that f of y applied f of x times is equal to f of x applied f of y times. And now with this is something that's actually cool, interesting. It's something that's more tangible. It's not just an injection, which is very nice that we have, but it's something I can work even more with. Now, where are you going to take this problem? I invite you here to pause for another, 5 to 10 minutes. It really depends where you want to take it. There are a lot of solutions to this problem. I'm just giving you sort of where my thinking is leading me now, which is not necessarily where it led me when I first saw the problem. So for me right now, I'm seeing okay, I have an injection. I have this. Well, if I set y is equal to x, I'm getting nothing. Well, what happens if I set y is equal to some f of x? Maybe f of x applied L times. Well, then this thing right here becomes f of x plus L. Right? How do I know f of x plus L of x? How do I know it's f of x plus L? How do I know that I just add the L? And my thinking is if it's a 0, then if L is 0, then it remains the same. It's just f of x. And it's just f of x applied f of x times. If it's a 1, and then if it's a 1, I'm applying it one more time. That's how I'm getting it. And here I'll have is equal to f of x applied f of x to the power of L times. And now what's the thing? I have this rule. If fk of x is fl of x, then I have the absolute difference. So now here what I have is the absolute difference is equal to, I'll have f of the absolute difference of f of x plus L minus f of L of x is going to equal x. So now I have this holds true. And it seems good, like everything's nice. And in fact, this should be 0 for me. Right? This, like, in our solution, this is equal to 0. FL of x is equal to f of x plus L. So, how do I now deal with this? Is a question. Actually, is this the same? Let me just double check this. If L is equal to 0, I have an x here. So wait a second. Something's fishy right now. Let's pause for 2 to 5 minutes and figure out what the next step is. Okay, here was the mistake. And this is why it's good to sometimes pause and double check, like, wait, is the solution there? Is the solution good? I made a mistake. When I plugged this in here, I plugged it in here, I forgot to add, I'm applying another f here. So there's f of L plus 1 in here. And now everything makes sense. Now for a second I was like, wait, what? I'm getting f of x is x. So, and this holds true for every x and every L. So now this is interesting. And namely, if I plug in 1, all I'll get f of, like, nothing is equal to 1. Like f of nothing is 1. So this thing has to be 0 for x is equal to 1. So we have f of 1 plus L is equal to f of 1 when you apply it L plus 1 times. And this also seems like, hey, if I get f of 1, well, finish the problem. Pretty much, I'll be done with the problem if I just get f of 1. Because now this is just done. That's just it. Because if f of 1 is 2, I'll just plug in L is equal to 0. Actually, I'll plug in L is equal to 1. And I'll get f of 1 is equal to f of 1 plus 1. And this is 3, this is 2, this is f of 2. And then I can get every single one of these. So this thing is true. Now, f of 1 plus L is f of L plus 1 of 1. And we get that just from the fact here that we had f of A is never equal to 1. So now with this, we have injection. What else can we do? Well, this sort of tells us that this f applied as many times as you want on 1 is never going to get to the same thing. It's never going to get back to, there are no cycles here. So that might be a bit advanced. Maybe we don't need that. And because there are no cycles, if there was a cycle, then you would change the L's and you would have, this would shut up. This would just be 2 different values for the length of the cycle. Like if the length of the cycle was P, then F1 plus L and F1 plus L plus P would need to be identical for some L. So there are no cycles when we just keep applying F on 1. Though we still haven't really used this fact as much. And my question now is, could we use it somehow? And my thinking is, well, let's just say that f of 1, maybe let's think of the smallest number here that exists. And there's a number. If we plug in x equal to y equal to z equal to 1, we'll get a 4 here. So there exists an f of something, and just as f applied, f of 1 applied, f of 1 to the f of 1 applied, f of 1 times. So there is an a such that f of a is equal to 4. And now maybe we could go say, I don't know, actually, what we could go ahead and do. There's an a that's applied only 4 times. It feels small, but I'm still, like, that's a free, like a is free. I know that. Probably. I really, really think it's a free. Maybe I'm wrong. Maybe, is there anything we can do here for that a. So if f of x is equal to a, I have no way to figure out what this other thing is. So that's a bit problematic. I don't know. Here, I would invite you to actually pause for 20 minutes. Let me clear up the board and write down everything that it is we have. Okay, so now what I'm thinking is, wait a second, let me use, I didn't have to plug in y is equal to f of x, fl of x here to get this like cool-ish claim, right? It's not super duper cool, it's just cool-ish. Like maybe maybe I can even show that there's two, right? If I plug in x is equal to 2, then f of x, no, but it's this is meant to be 0 even for x equals 2, right? This is always meant to be 0 if we have the correct solution. This is x plus 1 plus L, and this is x plus 1, this is x is equal to x at the end of the day. So this is cool, but I think it's only cool so far as it gives us this. F of 1 applied L plus 1 times is f of 1 plus L for every single L. And this is L even 0, but every natural L. Like f of L equals 0 doesn't really give us anything here. But I saw, wait a second, we didn't use really much about this injection thing over here. Why not? Why don't we use this fact here? This is f, there's a lot of f's here. So now we have if f of y is greater than f of x, then we'll be able to apply the f all up until the moment that we reach a 0 here. And then we'll have f of y minus f of x in the absolute value of what? Of, here the thing is that we're going to be left with a y, and then f of x is going to equal that. F of x applied this many times is going to equal y. Does it also make sense? It's a question we keep asking ourselves. If this is y minus x, we're applying this y minus x times. We're going to add 1 y minus x times. That means we're going to add y minus x. 2x, we'll get y. All is good. There's beauty in the world. So we have this. And now, mind you, no two f's are identical. So from here, I think an argument can be made that so f of 1 needs to be less than everything else. Otherwise, you'll get f of something as 1, which we can't get. This is one reason why this is a cool function. I think it's a really, really cool functional equation because of this tower. But also f of 1 now. Look, you're using the fact that nothing is f of 1. Now f of 1 is going to be less than everything else. It's going to be less than f of k. So if we plug in x is equal to 1 and y is equal to 2, we'll have f of 2 minus f of 1 of 2, right? Of 1 is going to equal 2. So not only is there an a such that f of a is, where was that? F of a is 4, but there also exists another number, there exists a c such that f of c is equal to 2. Why do I want to get to 2? I want to get to the point where I'm not applying this function over and over and over and over again, right? That's what I want to get to. Actually, there should be none of these here. Now what do? This is a cool little problem, I think, because of this sort of, you don't know what you're going to do. There are so many things you can do, you don't know what you should do. And, okay, so now we have this. F of x applied f of y minus f of x times is equal to y. And this also means that every number greater than or equal to 3 is going to be represented. Right, for every y that we just plug in, x is equal to 1. But hey, wait wait a second, even more so to the point, can we now combine the fact that f of 1 of L plus 1 is equal to f of 1 plus L with this fact, right? Can we like sort of use those two together? Because now we have we can get anything for y, and we can set y to be equal to f of 1 plus L, right? This isn't going to be equal to 1. So for any y not equal to 1, we have f of 1 applied actually. If y isn't equal to 1, we have f of y minus f of 1. We have a 1 here. This is going to equal y. So now we have this on one hand. Now if y is equal to f of 1 plus L, then this will also be equal to f of 1 L plus 1 times. And now we have something potentially more interesting. So then this implies that this is f of, which one is bigger? This is f of 1 plus L minus f of 1 minus L minus 1. So this f of 1 here is equal to 1, which we can't have. We can't have f of anything be 1, so this here needs to be 0. So we have f of 1 plus L is equal to f of 1 plus L plus 1. Okay, wait a second. Now f of 1 plus L plus 1. This is equal to f of L plus 2 of 1. F of this is equal to f of this. So okay, I'm back to square one. I thought I was going to get something different here, but no, I could have gotten this. So maybe this is a thing we could use. We could apply f of something in two different ways. That's another thing we could do. Also, what happens when we set x to equal c? Really, what happens when we set x to equal c? We get f of f2 of y of z is equal to y plus z plus 1 plus c. It's not nothing. Oh, though, wait a second. If c isn't equal to 1, then we can set c here, right? F of something is 2. If c isn't equal to 1, then if I put c into this equation, f of y minus f of 1, if I put y is equal to c, then I will get 2 minus f of 1 of f of 1 is equal to c. Now, if f of 1 wasn't c, if c is these, so c, the 2, actually f of 1, yeah. So the 2 is the smallest thing we can get. If it wasn't the case that 1 then must be the smallest thing we can get. So f of 1 is equal to 2, and now we're done because f of L plus 1 of 1 is equal to 1. Let me just double check this argument, so let's clear the board. So what we have from clearing the board is from here, we get that from y equals 1, plugging in y equals 1, meaning that y is the smallest in the range of f. Right, it can't be anything smaller than 1, otherwise we would get a 1 on this side. Now, also this is here, f of y greater than f of x. Then we have, now plugging in x equals 1 and y equals 2, gives us that f of 2 needs to be greater than f of 1, because f of 1 is the smallest. Gives us there exists a c such that f of c is 2. Now, given that f of 1 is smallest and there doesn't exist a b which is equal to 1, and given we have an injection, we have f of 1 is equal to 2. And now from f of L plus 1 of 1 is equal to f of 1 plus L, we have via induction that f of n is n plus 1. How would I prove this via induction? Assume f of n is equal to n plus 1 for some n. Then for n plus 2, I'll just write this as f of 1 applied n minus 1. N minus 1, should I say? So this is going to, what do I want? L. So f of 1 applied n times is going to give us, on one hand, here, it's going to give us 2, it's going to give us 2 plus n minus 1. So n plus 1 is going to give us 2 plus n. And then here, this f of n plus 1, 1 applied f n plus 1 times, is going to give us f of n after we applied n times. Wait a second. After we applied n plus 1 here for an n, if I applied n times, I am getting what? What am I getting? If L is equal to 0, I get f of 1 is equal to f of 1. If L is equal to 2, if L is equal to 1, I get f of 2 is equal to 3. If L is n, I get f of n plus 1. So I get f of n plus 1 if L is equal to n is equal to n plus 2. Right. And this n plus 1 is also equal to f of, this is now 2 plus L, f of n minus, this is f of n times, this is f of n minus time, n minus 1, f of n, f of 1 applied. And so I first do the first n here, and I get n plus 1, and that's how I get what n plus 2 is. And now if we plug it into the original, we get that this indeed does work. It's an amazing problem. I really hope you tried it out. It helped me really deal with these sort of f's applied many times. And it's a cool, funky little problem. I really like it. So this finishes up our problem. And as always, thanks for problem solving.